Hello everyone and welcome to the 47th lecture of the course Advanced Structural Analysis. In the last week we formulated the problem of the plane truss members for the geometrical stiffness, and then we implemented in the last lecture the one example problem for the plane truss. Now with this lecture we will start with the discussion on the beam members. So we understand that the problem which we formulated earlier for the truss members was done with respect to the translational degrees of freedom. Now in the same manner there could be beam members also which could be subjected to the large deformations, and then how to adopt these large deformations for the beam cases, that we typically will try to see from this discussion. As a starting point, the discussion will be considered in the similar manner that we identify the kinematic conditions for the given system, we define the general equilibrium of the material system, and then we eventually move to identify the conditions of the material constitutive rule to identify the overall framework of the geometrically nonlinear beam problem. Once we are able to do it, then we will try to see that how do we convert the standard metrics of the tangent stiffness for the given system. So to start with, we have a beam problem which is subjected to say any kind of external load on it, and due to the load the system deforms. The displacements in the system are significant, which means that we are considering that the displacements are large in the given problem. As the system subjected to large displacements, we as a first case identify that what are the internal changes or the strains which are generated in the given system. Now from a beam perspective, when we are trying to solve the given problem, we are understanding that the system is under pure bending, which means that we are not adding the contributions of the shear in the given system, right. So that is why the shear deformations are typically not considered. Now as we considered the initial undeformed configuration, you can consider that this is the undeformed position of the given system. As the system deforms, the transverse normal, which is typically defined as the normal on the given reference axis of the system, that will deform, and from the initial position it will try to deflect to a new position in the given system. The deflection which it takes place in the direction of the axial length, that typically is described as the axial deformation of the given system or the pure stretching in the given system, whereas at the same time the system as the axial length is not going to remain along the same horizontal axis. So the transverse normal will also bend with respect to the bending of the given axial length. In situations where the transverse normal no longer remains normal to the given surface, we include the shear deformations also in the given problem. In this case we are not including the shear deformation, so we consider that the transverse normal remains normal to the reference surface, but at the same time as the reference axis have modified by the original directions of the reference axis, we considered that the transverse normal will also be having an inclined position, and due to this, corresponding to the original axis, now we will be getting any of the point which is say somewhere over here at the beginning of the process, say a point P. That point was supposed to be over here in the deformed configuration, but now the system point has first moved by the finite extension or the stretching in the system, which is u, and then it has also rotated, which is due to some rotation of the given transverse normal, and we say that if the transverse normal rotation is theta, the effective displacement which the given point is going to take will be u, which is the displacement of the reference transverse normal at the level of the reference axis, plus y, which is say the distance from the reference axis to the point which is located. Say if I consider that any reference point is at a distance of y in the given axis, so this is the position, into theta of the given problem. So if you just magnify this particular part of the given system, I can show it in this manner that the given system which was initially somewhere over here has moved with respect to the reference axis by this value, which is u, and now the point which is anywhere above the given reference axis, say at a position of y, will also be rotated due to the rotation of the transverse normal. So the point will be moving from this position to a new position over here, and that is what is typically located by the expression of y into theta in the given problem. So, we define that this is the overall displacement for the given problem, which we describe in a general sense. Now, as we also know that for the regular problems, if the shear deformation is not included and the transverse normal remains normal to the reference surface, the theta value, which is the rotation of the transverse normal, will be same as the rotation of the given axial line of the system, which means that as your system, as the beam is undergoing some of the change in the slope, the same angle will also be made by the transverse normal. So, with this idea in mind, I can consider that if the axial line has moved at a angle of theta, and which can be defined by the vertical translation of the system with respect to the x direction. So, I can easily define that theta is nothing but dv upon dx in the given system, and this gives me the basis to write that effective displacement of the given system is u bar plus y into theta bar. Of course, now I have added the bar, which is also defining that all of these expressions, the way we are writing, are located in the member configurations or the member coordinates. Maybe the geometrical configuration of the original structure could be a little bit different, and that is where we will require the transformation at a later stage. So, effective displacement for any point which is y distance away from the reference axis can be described by this general rule, which is u bar plus y into theta bar in the given problem. As we have already defined that theta bar is equal to del of v bar upon del x in the system. So, I can define the effective displacement at any point with this expression in the given problem. Now, using this idea, we can now go back to the expression of the strain in the given problem, and we realize that the strain in case of the standard system of a beam, which is only having the variation with respect to the x direction, because now we are considering beam in this our present analysis as a simple part of the skeletal system. So, only along the x direction, or I should rather say that x of m direction of the given system, the parameters of the system are variable. So, that is why I can define the strain as a general expression del of u upon del x, which is the strain expression with respect to the effective value of the displacement, plus half of del of u upon del x square whole square plus del of v upon del x whole square in the given system. So, this is the standard large deformation strain relationship which we typically define. If you recall, in the last session also, when we were doing the derivation for the truss problems, we said that the derivation for the truss can also be evaluated from these standard cases. In this course, we are not going with the derivation of this particular equation, but in most of the solid mechanics courses which we do in the very starting of the postgraduate program, the standard large deformation, large displacement strain expressions are defined, and with this part we now identify that strain of the given system can be written as, using the same expression, that del of u bar upon del x plus y into del square v upon del x square, which is the corresponding strain expression on the given part. Then I can define the expression with respect to the second part, and I realize that the contribution which I am going to get with respect to the square term of du upon dx should be small, should be very small, as the changes along the length direction are not very significant, whereas the transverse deflections are significant. Okay. So, what it is driven by the idea, if I am saying that the large displacement and say this is the part of the beam, then the displacements are large not because the member is stretching significantly in one direction, but the displacements are large because due to the external load, the system is going with the significant amount of the transverse deflection. So, this also should be understood that in most of these cases, the axial deformations in the system are not considered to be large, but this is the transverse deformation, like under the application. A beam problem is a transversely loaded problem. So, if the transverse load is there, so the significant amount of deflection which we will typically see will be in the transverse deflection of the system, but still at the same time I can consider that along the length direction the changes in the system are not so significant. So, with this idea I can consider that this part of the system is insignificant or nearly neglected, and we have only one part of the large displacement based strain contribution, and that is with respect to the del v upon del x square in the given system. So, with this point we now understand, and in fact I will now write them all in the local coordinates. So, this is the expression which we describe for the given system. Now, with this point in mind, we have the two terms, one which is del u bar upon del x, and the second this nonlinear term, which we will keep together, and we call them together as del u bar upon del x plus half of del v bar upon del x whole square, whereas the second term, which is the multiplier of the y, we keep separately and we write it as del square v upon del x square in the given system. So, this system is same as the curvature of the given problem, right. If we look at the physical significance of individual terms, we realize that the first term is the pure stretching in the given x direction, which is the change along the length in the x direction of the system. The second term is the change in the x direction length due to the transverse large displacement in the transverse direction. So, del v upon del x whole square is the strain in the direction of the x itself, but it is due to the large displacements being taken place in the transverse direction of the given system. And the second term, which is over here, y into this parameter, is the curvature of the given system, because it is taken as the one order derivative on the slope, and that is where we end up with the two individual terms, which we call as epsilon x naught of the given system, and this term we call as curvature x of the given system. So, overall expression of the strain, which was written over here, can be now written as epsilon x naught plus y times curvature y of the given curvature x of the given system. So, with this point in mind, now I can express the given form in this manner. The first part of the system, the way we define, we express the standard expression, we substituted the value of the u, and we got the expression in this manner, which is the epsilon x naught if the given problem and the curvature term of the given part. Just to consider them individually, we take the 1 into y as a separation point, and this expression we identified only as a function of the x in the given system. So, what is now important to understand that the typical beam problems, when we will try to solve, will be solved only along the longitudinal or the x direction of the given system. The y direction of the system in the beam formulation will not be added. So, we just separate the variables with respect to the y parameter and the parameter of the x in the given problem. So, these are the parameters which we typically call as the strain parameter at the reference axis of the given system, and these are the one on which we will try to formulate the remaining part. Whereas, this is the overall strain, which typically defines that if the strain is being located at any point which is other than the reference axis also, then what will be the value. So, which will also be a function of y, and accordingly we can evaluate the value of the given system. So, with this idea in mind, now we move ahead with the problem. We have identified the strain terms and we have defined these strain parameters in terms of the function of the y and the function of the x separately in the given problem. As we should also note that we are only looking for one possible strain, which is the longitudinal strain in the given problem. We are not considering the shear deformation. So, that is why the shear strains or any other strain of the system are neglected in this case. Now, as the next part, we move to identify the equilibrium conditions. To identify the equilibrium condition, we use the standard total potential energy form. We know that this is the total potential energy. To get the equilibrium equation, we minimize the total potential energy of the given system, which means that we get del u minus del w equal to 0 in the given problem. Now, this del u, which is the strain energy of the given system, so small change in the strain energy, whereas del of w is the change in the work done of the given system. So, we identify these two parameters for the given problem. The strain energy, if we define for the given problem, can be located as the stress into strain in the given problem, but now we could have more than one parameter of the stress and strain. So, that is why I think if you recall the very first discussion in the beginning of the course, we describe it in terms of strain transpose into sigma of the given problem. As we are taking small variation, we take that variation on the del epsilon transpose, and this gives us the overall strain energy associated with the given problem. Similarly, the work done will be evaluated, which is with respect to the nodal values of the given system. So, if the element of the beam is identified, at the ends of the given system we will define the displacements of the given problem. We will note later that these displacements are located as u1 bar, v1 bar, u2 bar, v2 bar, and at the same time we also have the theta 1 bar in the given system. Of course, theta 1 is not an independent parameter, but that is defined as the derivative of V1 parameter of the given system. So, I can call it as del V upon del x at the point 1, and this could be defined as del V bar upon del x at the point 2 of the given system. So, these are the 3 degrees of freedom which have been defined at each of the node of the given system. So, corresponding to these degrees of freedom, what are the forces? If I describe them as the P bar in the given system, so I can describe the overall expression of the strain energy work done by the del U transpose P bar in the given system. Now, this has all been done in the local coordinate, that is why I have still put the bar sign on top of these given expressions. So, now utilizing this expression, I make the equivalence between both of these parts. As I start with the process, we have the del of epsilon transpose. So, I will substitute the values which I have just obtained in the previous case for this. So, del of epsilon x can be written as, so if you recall the value which we have obtained over here, it was identified with respect to 1 and y, and the individual expressions which are the variations in the given system. So, these are del of epsilon x naught and del of curvature x of the given system. So, as we obtain these values of the problem, I can write the expression of del of epsilon transpose into sigma x into dV in the given problem. Now, we also understand that sigma x is identified in the given problem as E into epsilon for the given system, as it is a elastic system for the given problem. So, we are considering that the elastic properties of the system are still linear, and the strain expression will further be written with respect to del of epsilon x transpose E into epsilon x in the given problem. So, this is the first parameter of the strain term which I am defining, strain energy part of the given system. Now, as I substitute the given system of the del epsilon transpose, I get this parameter as del of epsilon x naught del of curvature x into 1 into y in the given problem. So, I just did the transpose of this part, it will go with the transpose of the first and the transpose of the second, and accordingly we have modified the expressions in this manner for the given system. So, once we identify the matrix or the terms in this manner, I go with the further multiplication E into epsilon, and epsilon expression again I substitute 1 into y, and accordingly it will be further multiplied with the parameter of the epsilon x, which is epsilon x naught into curvature of x in the given system, and this is being done with the overall volume integral in the given system. Now, what we understand, as we are doing this with respect to the overall volume integral, the system can be considered with respect to the overall area integral into dz d of x in the given problem, considering that the member length is along the x axis, and corresponding to the given cross section we could have any of the area which will be now integrated with respect to the given problem. So, now what we do, we identify the given terms as del of epsilon naught. So, what we can write for this parameter, if we go back to this equation, we can say over here itself that this is 1 into y, and this parameter we can express as epsilon transpose epsilon in the given problem. So, this epsilon refers to the two parameters which are defined at the reference of the given system. This is also a vector contribution of the given system which we have identified. So, in this expression now, if I write the expression in this manner, I can call it as that this is epsilon transpose in the given problem. Over here I get this as a multiplier first, and this is the second component of the given system. So, I will do this multiplier first, 1 into y into E, 1 and y again, and this is getting multiplied with the strain expression of the given system. So, this is again identified with the strain part, this is epsilon transpose, and this overall will be going with the dA into dx integral of the given system. Now, if we just multiply this parameter, we understand that epsilon transpose into this part will give us E into y into E, y into E over here as well, and y square into E in the given part, and this will be further multiplied with d of A into dx in the given problem. Now, as a simple part of the procedure, we understand that epsilon as both of the portions of the given system which have been identified over here is only defined as a function of x. So, the dA integral can be completely provided to the expression which is identified over here. I do not need to provide the dA integral to the remaining portion of the given system. So, using this idea, I consider that the strain energy expression or del u part can be written as the del of epsilon transpose into the integral with respect to the area on the parameter of E into y and y square into E for the given system, and this is overall area integral for the given system. And let us just put this within one part of the bracket, and this is multiplied by E into dx, epsilon into dx in the given problem. Now, as we go ahead with the given system, what we understand that del of epsilon transpose, this overall parameter, as we realize that the d of A, which is the cross sectional system for the given beam, in this case we are not considering that the cross section has any of the width dimension, we can consider it to be 1 unit for the given problem. So, the integral of the d of A can also be considered as that if the dimension of the, if I just consider that this is the cross section of the given geometry and the width of the given system is already considered to be 1 unit of the given problem. So, I can consider that d of A is equal to 1 into dy in the given problem. So, if I do this integral for the given problem, or even if I go with the simple dA integral in the given system, I realize that this comes out as E into A as a first integral in the system. The second one, which is E into y into dA, that comes out as the first moment of the given area, in fact y into dA with the E multiplier, and over here we get y square into dA into E, and this is the second moment of the given area, and this is multiplied with the strain expression which is only a function of x with the overall integral in the x direction. I further write this expression as del of epsilon transpose. EA is fine, that is already evaluated. If I take the first moment of area for the given system with respect to the y direction, we realize that the given system, if it is considered with respect to the reference about the middle axis, the integral with respect to minus h by 2 to h by 2 in the given direction will eventually lead to the first moment of area being 0, and that is where we get both of these terms 0 in the given problem. The second moment of area y square into dA, if I calculate, this will give me the I value of the given system. So, this is the I value about this axis, which is the axis z of the given problem, and that is what we know that this is the E into I of the given problem. So, of course, I am not writing IZZ, considering that we have already an understanding that if it is a beam problem, the bending will be taking place about the normal to the given plane, and that is the axis z into epsilon into d of x in the given problem. So, this comes out as a standard expression of the strain energy which we have obtained for the given problem. I can call it that this is equation 1. Similarly, the expression of the work done can be represented with respect to the del u transpose into p bar in the given system. Now, del u bar we have already identified will be containing all the displacements of the given system. So, this contains the del of u1 bar, del of v1 bar, del of theta 1 bar in the given system, as well as the del of u2 bar, del of v2 bar and del of theta 2 bar in the given problem. So, these are the 6 values of the possible displacements which can exist at the 2 nodes of the given problem, and along with that we have identified the forces in these directions, and those forces we can now define as the force along the direction of the x in the local coordinate, force along the direction of y in the local coordinate at the node 1, moment along the direction of at the node 1, and that moment will be of course in the direction about the axis z. So, I can call it either as a mz1, or we can either simply call it as a m1 in the given problem. And similarly, we can now say that p of x2, p of y2 and p of z2 in the given problem, and this comes out as the overall strain overall work done for the given problem. We have of course not defined these values individually, but we can now correlate that the standard work done and the strain energy expression can be substituted to give the condition of the equilibrium of the given system, which means that now using this standard form I can write it as del of epsilon transpose E A 0 E I into epsilon, which is again the expression, into d of a, and this is equal to d of x, and this is equal to del u bar transpose into p bar in the given system. So, with this idea we can consider that now this is the expression which we can identify for the evaluation of the equilibrium conditions of the given system. Now, as a next step we can identify that what is the material constitutive conditions in the given system. So, to identify the material constitutive condition, we utilize the same expressions which we have just obtained over here. We realize that these expressions can be correlated with the strain expressions which are located in this manner, and they can be correlated with the overall part of the forces in the given system. So, if I call that this is the part of the strain vector of the given system, so this overall part of the system can be equated with respect to the force of the given problem, and that is what we bring as a S of x, which is the axial force in the given system, m of x, which is the moment force in the given system, and that is totally equal to E A 0 0 E I into the strain vector, the terms associated with the given system. While doing it, we have now converted the whole problem into a simple skeletal form. That means, in the whole expression now the expressions are only in terms of the x parameter, and the dependence on the y parameter has been completely avoided. With this idea in mind, we can now understand that the standard vector which we define over here can be called as the S vector of the given system, which contains the forces. And now, in the case of the beam problem, it has the axial force as well as the moment force in the given system. So, now one can consider that the given problem which is being designed is subjected to these two internal member forces. One is the axial force and second is the moment of the given system. Now, this is one important aspect of the nonlinear beams. The regular beam problems which we were doing earlier, we were considering that the degrees of freedom were assigned in this manner, but we were not considering the axial degrees of freedom in those cases. But as we go for the large deformation cases, we understand that the axial degrees of freedom or the axial forces become important to bring the instability in the given system. In fact, any kind of the axial force is the responsible one which will bring the geometrical stiffness contribution in the given problem, and that is where the contribution of the axial component or the axial force has been included in the given system. And these kind of cases could be a very simple example of the problems where we call something as a beam column members, where there are members which are subjected to the axial forces and at the same time the moments in the given system. So, those systems can be easily defined by these kind of cases, because now they have the provision of the axial force which is S of x as well as the provision of the moment in the given system. Now, this expression can be written as S, which is this part of the vector, into k naught, where k naught happens to be this parameter of the given system, into epsilon, which we have already defined as a vector in the given system. Now, we understand that k naught is a constant value, whereas the epsilon value is a function which is dependent on the displacement parameters of the given system. So, we write finally that k naught into function of u bar, that is the expression which we are getting from here. Now, if you recall the expression previously, the way we were doing in the previous truss problem, we identify the small variation in the S, and that was written as k naught into del epsilon, which was the internal changes in the member system or the internal deformations of the member system, and they were expressed in terms of the A into du bar, where A was the connecting matrix or the connecting vector for the system which was defining the values of these member deformations in terms of the nodal displacements of the given system. Now, what we have not got here is the value of the A matrix. We eventually will now need to look for the value of the A parameter, which will be required to calculate the internal member deformations in terms of the nodal displacements of the given system. So, that is what we will try to see in the subsequent session, that how do we obtain the value of A in the given problem. Of course, now this is not as simplistic as the truss problem. We have to make some assumptions, and that is where we bring the simple concept of the shape functions in the given problem. And with this point in mind, we understand that the problem formulation is very similar to what we did for the truss problems as well. Only difference is that as the beam problem has the general constitutive kinematic terms, we adopt a strain energy based formulation which appears to be more easier to define the equilibrium conditions of the given system. With this, we stop over here. Thank you everyone.